In Chapter 9, we're going to use what we learned about infinite series in Chapter 8 and create series to represent different types of functions. The reason that we might want to do this is because one of the first things we're going to talk about here are power functions. And power functions are pretty much just polynomials. They could be infinite polynomials or they could be finite polynomials. But no matter how far you extend these, the bottom line is they're just a polynomial. And we can estimate a lot of functions pretty accurately using these power series, such as natural log or e to the x or sine x. If you remember back in Calculus 1, we had to learn special derivative and antiderivative rules for all of those special types of functions. But then there was just one rule for finding derivatives and antiderivatives of polynomials, and that was the power rule. So one benefit of learning power series is we can estimate all of these other crazy functions just with a polynomial. So let's start just with the definition of a power series, and basically all this is a polynomial where the power gets larger and larger. And like I said, it could be infinite. We could say that our series is going to go to infinity, or we could choose to just use a few of the terms. If we do that, we're not going to get an exact answer, but sometimes an approximation is good enough. So the math notation for power series is the sum from k equals 0 to infinity. So this one's going to go on forever, of c sub k times x to the k. Now the c is just a coefficient, and that little subscript just means every single term could technically have a different coefficient. We're just matching it up with the x value that has that same power. So if you were to plug in c equals 0, x to the 0 is just 1. So all we get is a constant term. If you plug in k equals 1, you get c1 x to the first, or just x. If you plug in 2, you get c sub 2 x squared. And then this just keeps going forever. Like I said, we could choose to stop it earlier if we don't want an exact representation of our function. If we just want an approximate, we can choose not to extend it out forever. A little bit more general form for a power series. There's one additional thing we may see. We may actually see x minus a to the k instead of just a x to the k. And I'm just going to write a few terms of this out as well. Looks very similar. So instead of the x's, we have x minus a's. Now the only difference with this one is we say it's a power series centered at a. And there are some functions that we're going to approximate that we have to center them pretty close to the value that we're trying to approximate, otherwise it's not going to work. So this one here is centered at A, and we'll talk about more what exactly that means. But really, these are saying the same thing. These are power series. When we write them out, they just turn into polynomials. The first one obviously has nothing subtracted, so we could say that it's centered at 0. Which is a pretty common thing to do, but there might be some cases where we have to center it somewhere else. And in order to center it somewhere else, we just subtract that from the x. So we'd say x minus a in all of the x spots. So like I said a moment ago, one of the main reasons we do this is so that we can come up with a polynomial approximation for functions that we don't typically write as polynomials. And one example of that is, let's say, the e to the x graph, which looks like this. Every time we want to find a power series, we have to identify the center. Now, there are some cases where we could center it anywhere we want and it wouldn't make a difference. There are other cases where the center is really important. So just for this example, I'm going to say we're centering it at x equals 0. Now, if I just found a 0-degree polynomial, we're going to call this p sub 0 of x equals, this is going to be a 0-degree polynomial. And 0 degree means no x's. That means we're just working with a constant. If I tried to approximate f of x equal to e to the x with a 0-degree polynomial, all I would come up with is a straight line, y equals some sort of constant, and we have to have that center so we know where to match them up at. So that point there is actually 0, 1. And if I want my 0-degree polynomial to match up with that one, it needs to at least share that point. So that would be our p sub 0 of x. It's a straight line that just matches up with the value at our center. We can see, looking at the black graph and the red graph, that they are not very similar. Probably around 0, 1 they're pretty similar, but as we move away from the point 0, 1, they're not similar at all. So this approximation would be even better if we did a 1st-degree polynomial. So if you think about what a 1st-degree equation looks like, that's going to have an x to the 1st and possibly all the terms that have lower degree than it. So a 1st degree and a constant. That's just a straight line. Now it could have some slope to it. It's not necessarily going to be a horizontal line. But what this means is I not only want to match up my point, I also want to match up my slope, because 1st-degree equations are linear equations and they have a slope. And our approximation would be much better if we matched up the slope at this spot. And it just so happens that the slope of e to the x at 0, remember we do slope by doing derivative, the slope is 1. So I want a line that has a slope of 1 and a y-intercept of 1. And this is our p sub 1 of x, which ends up being 1 plus x. Intercept of 1, slope of 1. And you can see that at least to the right of the point 0, 1, that our black graph and our blue graph match up pretty nicely. So it's a better approximation. It's still not great though. And just for the sake of it, I'm going to do one more. If we matched up, or if we found, it's not equal 1. Oh yes it is. If I wanted to find a 2nd-degree polynomial, so I'm going to say p sub 2 of x is a 2nd-degree polynomial that matches up with e to the x. We want the point to match, we want the slope to match, and then remember slope is 1st derivative, so 2nd-degree polynomial is going to match up our 2nd derivative. So do you remember from Calculus 1 what we use 2nd derivative for to identify on our graphs. Second derivative is used to identify concavity. So it's going to take me a little bit more calculations to figure this one out, but I believe, and we'll pretend that goes through. This would be our p sub 2 of x, because we now have a second degree equation, which means it goes out to a x squared, which means it's a parabola. Now this green graph has some curve in it, just like our original function did, so that's going to be an even better approximation. And we can continue this on forever and figure out what a third degree match would be, what a fourth degree match would be, and so on. And you don't have to do it by guessing. There's a specific formula that we're going to use that's actually going to make figuring out these polynomials really easy. So our goal here was to just find some polynomials that match up with f of x. First we started with just a constant, so that just matches a single point, that's p sub 0. And then we did a first degree equation that's going to match the point and the slope. And then we did a second degree equation which ends up as a parabola. So now we've got some curvature in it as well, which is going to be even better because our e to the x graph has some curve in it. So in general, the farther you go out with your polynomial, the better the approximation that you're going to have for the original function that you're using. So the formula that we use to find these, so that's not just a guessing game, is called a Taylor polynomial. And the formula can look pretty overwhelming, but once I explain it a little bit, it's not too bad. So if we want to find the Taylor polynomial for f of x centered at c equals a. This is what Taylor says we need to do. So I'm not going to identify any particular degree that I'm going to go out to right now. I'm just going to say some arbitrary degree. We know it's got to match the point at c equals a. And the way that we do that, it's not going to look this first term is not going to look very intuitive, but it will work out nicely. We do f of a times x minus a to the 0 all over 0 factorial. Now, why in the world we would do the 0 power and the 0 factorial? Just so that you can see a pattern with our other terms. But really, f of a is the functional value, and that's exactly what we matched up here on our e to the x graph. We just matched up our functional value. Anything to the 0 power is just going to be 1, and 0 factorial is equal to 1. So they're all just going to multiply or divide out anyway. But I write those just because I want you to see the pattern that we're establishing. Now, if we want to go out another term to a first degree, you're going to do your first derivative evaluated at your center, x minus a to the first power all over 1 factorial. If we're told to find a second degree polynomial, we're going to go out to the second derivative times x minus a squared all over 2 factorial. So hopefully now you're starting to see the pattern. So we can extend this out to any nth degree that we're asked by going out to the nth derivative evaluated at our center times x minus a to the n all over n factorial. So let's look at what exactly this would look like with the graph we did above, because I did not give you the second degree polynomial match. I just said this would be p sub 2, but I didn't say what the formula would be. So we're going to find p sub 2 of x. Which means I need to go all the way out to my second derivative. You always include all of the terms before it. So there's a little bit of preliminary work that we need to do before we can just jump straight into this equation. We need all of the derivatives evaluated at the center. So we need the original function, the first derivative of e to the x is just e to the x, and we need the second derivative, which again is just e to the x. And then we evaluate all of these at the center, and e to the 0 is just equal to 1. So f prime of 0 is just equal to 1. F double prime of 0 is just equal to 1. So this is giving me my coefficients here. It's giving me my coefficients for this Taylor polynomial. And then for the other pieces, those are just standard every single time. It's really just the coefficients that are going to change, and then the a value at your center. And ours is centered at 0. So to set up p sub 2 of x, we're going to say the original function evaluated at 0 times x minus 0 to the 0 over 0 factorial. And I'll simplify all this in just a minute, but I want you to just have another look at this pattern. And then your first derivative evaluated at 0 times x minus 0 to the first all over 1 factorial. And then your second derivative evaluated at 0 times x minus 0 to the second power all over 2 factorial. So these 1's are coming from here. And then the 0 inside with the x is because that's our center. And it's also being used when we evaluate for our coefficients. But we can clean this up quite a bit because all those 0's and 1's don't really make a bit of difference. So this entire first term just simplifies down to 1. For the second term, x minus 0 is just x, and we have x to the first power. We have times 1 in front and divided by 1 in the bottom. That means it's just a plus x. And then for the last piece, x minus 0 is x, and we've got that squared, times 1. 2 factorial is 2. So we've got 1 over 2. So this one's got a 1/2 coefficient. So we've got 1 plus x plus 1/2 x squared. This is our second degree polynomial approximation for e to the x. And it's very important to say that it's centered at 0, because it would look very different if we centered it somewhere else. Now let's check and see how accurate our polynomials are. We already said that p sub 1 was just going to be 1 plus x, and p sub 0 was going to be 1. Now let's use these to find an approximate value and we're going to do all 3 of them to approximate e, and we need to do something fairly close to the center, otherwise it's not going to be a good approximation. So I'm going to say e to the 0.1. So that's pretty close to 0. First, let's look at the exact value. So f of 0.1, this one's obviously something we would have to do in our calculator. And I'm going to keep as many decimals as possible. And my calculator says this is about 1.105170918. There's no way that you could calculate that by hand unless you've got some magical brain that has memorized every single possible value of e. The nice thing about the polynomials are, the only operations we ever have to do are powers and multiplication and addition and possibly subtraction. And if we absolutely had to, we could do that without a calculator. So these polynomials potentially are much easier to calculate. So now let's compare. Remember, p sub 0 is always equal to 1, no matter what we plug into it. P sub 1 is 1 plus whatever we're plugging in. So 1.1. And then p sub 2, we said, is 1 plus x plus 1/2 x squared. And I get 1.105. So you can see as our polynomial gets larger and larger and larger, these values get closer and closer and closer. So right now, with p sub 2, I am accurate all the way to the thousandths position. The exact value for e to the 0.1 and my polynomial match all the way to the thousandths. So that's pretty good with just a polynomial that has 3 terms in it. There's also something called absolute error that we could check. And absolute error is exactly how far off you are from the actual value. So we're going to do this for just p sub 2. The absolute error of p sub 2 is f of x minus p sub 2 of x. And we've got absolute values around there because we don't really care which one's bigger, which one's smaller. We just want to know how far apart they are. So f of x is the exact value that we'd most likely have to get from our calculator. P sub 2 of x is the polynomial approximate that we got. So for the exact, we had 1.105, 170918. And then for my approximate, I just had 1.105. Which means when we subtract, and you always want a positive number for your absolute error, that's why you have the absolute values, we get 0.000170918. It is very common for this number to be written in scientific notation because it's usually going to be very small. So we could also say that this is about 1.71 times 10 to the negative. Now we move this to see how many times it takes us to get there. And we went 1, 2, 3, 4, 10 to the negative 4. That's our absolute error. That's how far p sub 2 is from the exact answer. So it's pretty good. Like I said, we're only off by, we match to the thousandths, so we're off by 1.71 or 10 thousandths. 1.71 10 thousandths is how far we're off of the exact value. So I'm going to switch over to Desmos here and then just show you a better picture rather than my my rough little sketch up here that I had, especially because I think my parabola is off a little bit. Now that we have the exact p sub 2 function, we want to compare this to what our e to the x graph looks like. So for the first one, and I'm hoping that the this will allow me there we go. I want that e to the x. So that's what we're trying to approximate, that e to the x right there. And first we found, oh, it went away. There we go. See if it goes away again. No, okay, it stayed this time. First we did a constant function of just 1. There we go. We got y equals 1. And they did that in orange. And we can see all they really have in common is that single point. And then we did our linear function, y equals 1 plus x. And that's better. We can see that they still have the 0, 1 point in common, but you can move a little bit farther away from the 0, 1 and they still match up pretty good. So if we zoom in on this, you can see that right away, besides having the single point in common, the red graph follows the e to the x graph kind of away from the 0 point longer than the orange graph does. The orange graph really has nothing in common besides that single point, but our linear equation starts to follow it in the same direction that it's moving, and that's because the slopes match. And now let's look at the quadratic function, see what that looks like. We had y equals 1 plus x plus 1/2 x squared. And they've done that one in purple. And the purple graph follows our e to the x graph even better. Maybe not so much on the left, but certainly on the right. You can see that they stick together there for quite a ways. So the x squared graph is an even better approximation than our constant and our linear function. And if we could go out to a cubic function, that would be even better. And then a quartic function with a 4th degree, it would be even better. Just as a general rule, the more terms or the higher power your polynomial goes, the better it's going to be as an approximation for your original function. So let's try one more. Let's find p sub 0, p sub 1, and p sub 2 for g of x equals natural log of x centered. Now we can't center this one at 0 because natural log of 0 is undefined. We're going to center this one at x equals 1, or at c equals 1. Now, notice up here when we did these that these terms match. Every time we go out an additional term, everything before it stays the same. So when I did my p sub 2, it had my p sub 1 in there, and it had my p sub 0 in there. So you don't have to find 3 different things here. I'm going to jump straight to my p sub 2, and then I'm just going to pull terms off of it to identify my p sub 1 and my p sub 0. So remember, we've got some preliminary work to do. First we got to figure out our coefficients, and that is our function and its derivatives evaluated at the center. So we're going out to the second degree, which means we have to go out to the second derivative. So the original function's natural log of x. The derivative for natural log of x is 1 over x. Since I've got to do the derivative for that again, it might be easier to write it as x to the negative 1. And then you can see you just do second derivative by doing power rule. So you get negative x to the negative 2, or negative 1 over x squared. And then we need to evaluate all of these guys at our center, which is 1. And this gives us our coefficients for our polynomial. So natural log of 1 is 0. G prime was 1 over x, so 1 over 1 is 1. And G double prime was negative 1 over x squared, so there we're going to get negative 1. And then after that, the other two pieces that we see in our polynomial approximation are the same. We do x minus our center to a larger and larger power over factorial to a larger and larger power. I'm actually going to start with p sub 2, and then just take pieces off of it for my other guys. So p sub 2 has the original function evaluated at the center times x minus the center to the 0 over 0 factorial. And then first derivative evaluated at the center, x minus the center to the first power over 1 factorial. And then second derivative evaluated at the center, x minus the center to the second power over 2 factorial. And we'll clean this up a little bit. Now this whole first piece is going to zero out because I'm multiplying by 0 up there in my numerator. So we're not going to have a constant term. In my second piece, I've got a times 1 and a divide by 1. So we're really just going to have that x minus 1. And then my second piece, I'm adding a negative. In the top, I've got a negative 1 coefficient. 2 factorial is equal to 2. So this is minus 1/2 of x minus 1 squared. And you do not need to FOIL that out. You can leave those, and you should leave those x minus 1s intact. Do not attempt to FOIL them out. This is our p sub 2 of x. Now for p sub 1, we're only going to use out to the linear piece, so just the x minus 1 piece. And then for p sub 0, we're just going to use the constant piece. Remember, the constant piece was 0. And then we're going to evaluate all of these at a point close to 1. Let's say we're going to evaluate them. It's got to be pretty close to our center, otherwise it's not going to be a good approximation. So let's evaluate all of them. And the way that you're actually going to see this in the homework is going to say use p sub 0 of x, p sub 1 of x, and p sub 2 of x to approximate natural log of 0.95. And then we're going to find the absolute error for the p sub 2, just the p sub 2 function. So we're going to see what the polynomial tells us is the value at 0.95. And hopefully it's going to come out really similar to what the exact value is when we ask our calculator what natural log of 0.95 is. But first, for our second degree polynomial, we're just plugging 0.95 in for x. So if I do 0.95 minus 1, I get negative 0.05 minus 1/2 of negative 0.05 squared. And for my calculator, I get negative 0.05125. If I plug it into just my first degree polynomial, then I'm just doing 0.95 minus 1, which is negative 0.05. If I plug it into my 0 degree polynomial, remember the 0 degree polynomial is always equal to 0. So we've got 3 different approximations for the natural log of 0.95. Let's see what the calculator says this value actually is. According to the calculator, the natural log of 0.95 is negative 0.05129.32944. So that's pretty close to 0, but negative 0.5 is even better, and negative 0.5125 is even better. As we use a larger and larger polynomial, as that polynomial, the degree of the polynomial gets larger and larger, the approximation gets better and better. So now we're matching out to the tens, hundreds, thousands, 10,000s. So now we're off just in the 100,000ths position. So every function is different. We picked a value that was closer than in the last one, so that might be part of why we got a better approximation here. But for absolute error, we're going to see exactly how far away we are. This is the functional value minus the polynomial approximation. And we do absolute values around it because we don't care who's bigger and who's smaller. We always want it to come out positive. So we want to compare the original function value that we got using our calculator of negative 0.05129.32944 and subtract what we got from our second degree polynomial, which is negative 0.05125. And when we do this, we get a really small answer. At some point, your calculator might just give you scientific notation right off the bat. Others you may have to convert yourself. So the decimal here is 0.0000432944. Or scientific notation would be about 4.33 times 10 to the, I know it's negative because it's a tiny number, and just count how many jumps you would have to do to get past the 4. And we had to do 5 this time, so it's going to be 10 to the negative 5. So that would be our absolute error for our second degree polynomial, which is really good. Like we said, these two match all the way out. They match in the tenths, hundredths, thousandths. They match the 10,000ths. It's not until the 100,000ths position that they start to differ. So just by creating a second degree polynomial, we're able to come up with a pretty accurate value for a natural log function all the way out to exactly to the 10,000ths, and don't start seeing a difference until the 100,000ths.